Hello everyone, Mr. Record here, Avon High School. Going to take a look at a Continental Mathematics League problem from the 22-23 year. And this is in Meet 2, and it's the last problem, problem number 8. I'm going to read this to you real quickly. It says, Archimedes long ago proved that if A, B, and C are points on a parabola, and C is the point on the parabola enclosed in the parabolic segment at a maximum distance from AB, then the area of the triangle ABC is 3/4 of the area of the parabolic segment. You're given the equation of the parabola as y = x squared plus 3, and the coordinates of A are -1, 4, coordinate B is 3, 12, and that C is indeed the maximum distance from AB. We're asked to find what is the area of triangle ABC. Now, there is some terminology in this problem that might be a little new to you depending on where you are in the course. So first of all, this C is going to be that maximum distance. So if you draw like the perpendicular there, which really isn't important to the solution of the problem, but I just want everyone to know that C is as far away as it could possibly be from the actual line segment, AB. So in other words, if C were anywhere else along this parabola, it would be closer to the line segment AB than where it is currently located. Now, there's some terminology called parabolic segment, and that's the part here that I think is a little bit bothersome at this point. A parabolic segment would be a region that's enclosed by a parabola, and let's say in this case this chord or this line segment AB. So if you just kind of look at that highlighted region and just within the confines of the line and the parabola, that is what we refer to as our parabolic segment. Next, we're going to have to figure out what the area is going to be of this triangle ABC. But we're told, though, that the triangle's area is going to be 3/4 of whatever the area of our parabolic segment is, as we can see in this particular text. And so if we could figure out what the area is of the parabolic segment, we just have to perform a very simple calculation. And while Unit 8 in the course and exam description will address this very clearly, it's very possible that those of you that are watching this in your class, you may not have been exposed to this. So to find the area of an enclosed region, all that one has to do is to integrate the difference between an expression that would be the top of that particular bounded region. So this would be the blue line that you're seeing, minus an expression for the bottom of that region, which in this case would be the parabola that I'm highlighting in black. And then the boundaries of integration that we could use would just be the values where we intersect on the left side, the x coordinate at least, and the x coordinate of the boundary where we intersect on the right side. But long before we can start investigating that, we're going to have to find the area, or I'm sorry, the equation rather, of the line segment AB. Fortunately, that is going to be pretty easy. So for our equation of AB, we need two ingredients. We need a point and we need a slope. In order to find the slope, we just simply invoke our slope formula, which is going to take the difference of the y values, so in this case 12 minus 4, over the difference of the x values, 3 minus -1. In this case, we have 8 over 4, which of course is going to be 2. Now at this point, we can find the equation of our line quite easily by choosing one over the other of these points. I'll choose point A for simplicity, and I get y minus 4 is equal to 2 quantity x minus -1, or x plus 1 in this case. And then it will be in our best interest to go ahead and solve this equation for y, and maybe even distribute this 2 while we're at it. So if we distribute the 2, we'd get 2x plus 2, but by the time we add that y over, we would get y is equal to 2x plus 6. Now, as I said before, one of the easiest applications of area in calculus, or easiest applications of the definite integral, is truly finding the area between two graphs that enclose a region, rather. And so to make that happen, we're just going to take the definite integral of the quantity that is going to serve as the top boundary, and we'll subtract the equation of the bottom boundary, which again is the x squared plus 3. Not so much an equation as it is an expression. And all of that will be integrated with respect to x. Now we have to kind of tell this integral how to behave. Where do you start? Where do you end? And so we're going to start from the farthest left boundary, whose x coordinate is -1, and we'll go to the farthest right boundary, whose x coordinate is +3. And once you set that definite integral up, all things are ready to go. The CML will allow students to use the graphing calculator. So if you want to take this definite integral using your calculator, that would be okay. It's also quite easy to integrate by hand if you want to do that as well. But don't forget, there's one extra little step here. We're told that the triangle is only going to be 3/4 of that area. So hopefully that should be a pretty easy thing to apply and finish up.